So, good afternoon and welcome to this seminar today. So, as you have seen, the topic is about computing paradigms in connected vehicle networks. And our speaker today is Naercio Magais. Naercio has a PhD from IST in Lisbon, and he was best PhD student of Indus ID in 2019. So very promising young researcher. Currently is assistant professor at Lusófona University and is also an integrated researcher member of COPELABS Research Center. And as many of you know, there are some conversations between CTS and COPELABS, so that perhaps COPELABS can join CTS in the near future. So as such, during this series of seminars, we will have several presentations from colleagues from COPELABS, and Naercio is the first one to start with this presentation. So as usual, after the presentation, there will be a period for questions and discussion. And I asked André Rocha to be the moderator for this second part of the session. So let's start then. Naercio, welcome. And so the floor is yours.
Thank you. I'm going to share my slides. Good afternoon, everybody. My name is Naercio Magais, and I'm here to present or to make this presentation entitled Computing Paradigms in Connected Vehicle Networks. I would also like to point out that this presentation it's based on recently published.
E agora mudar aqui o.
Okay, I will continue. This presentation is based on a recently published research paper of one of my students. It was published in IEEE CAA Journal of Automatica Sinica in 2011. It's 2021, so this year. This presentation here, it's basically composed of these 7 parts, where first I will basically present the motivation underneath this research area. I will talk then a little bit about vehicular communications. Followed, I will present some types of connected vehicle networks. Then I will basically talk about computing paradigms in general, and then I will go into a more specific on how we can apply these paradigms, or they are being applied in connected vehicle networks. Then I will talk about security. Why? Because security is nowadays a very interesting research area, because it's basically transversal and there are a lot of security threats that are basically affecting many domains. Later on, I will present future directions and concluding remarks. When we are talking about these connected vehicle networks, it is always interesting to point out that the first International Congress on Intelligent Transportation Systems actually took place in Paris in 1994. And in the last 27 years, concepts such as cloud computing and Internet of Things, as we know them, also emerged. At the same time, due to developments in wireless networks, our physical systems, several areas of our lives have been flooded with technologies that actually we did not knew already existed, such as mobile computing, among others. But research in connected vehicle networks, it's actually a very critical area because it covers a category of things that supports businesses worldwide, and it is the means by which billions of people actually move around, whether by land, sea, or even the sky. Transporting consumers' goods efficiently and intelligently enables the economy to move globally, supporting, for instance, the international trade. However, we still don't have the sense that these vehicles are actually connected. They are actually truly connected, and that technologies that have been produced so far are part of our day-to-day life. Vehicles nowadays are becoming safer and smarter, but the use of inter-vehicle networks is actually not that popularized. But if we, for instance, consider a typical intra-vehicle network, which can be actually composed of 80 or more cyber-physical elements, such as electronic control units and sensors, we still don't have everyday clouds of vehicles doing computation while waiting, for instance, for the traffic light to open at an intersection. When we are talking about vehicular communications, we have here to consider basically inter-vehicular communications. We have here to consider these two most used categories. For instance, this DSRC, where we have the IEEE 811.p, wireless access in vehicular environments, and on the other hand, we have this new technology that is the 5G, and in specifically for vehicular networks, we have the cellular vehicular to everything, the CV2X. We have here to consider, and it's actually important here to consider that when we are talking about wave, it has already have had a solid development path since 2004, and are mainly used in one type of vehicular networks known as vehicular head-off networks. On the other hand, we have 5G that seems to offer technological novelties that meet the challenges proposed for METIS, that is the Mobile Wireless Communication Enablers for the 2020 Information Society, and the ITU, that is the International Telecommunications Union. When we are talking about these challenges, we can, for instance, mention here low latency, high reliability, high throughput for METIS, and for instance, for ITU, we can mention here, for instance, latencies below 1 millisecond, or even transfer rates between 100 megabits per second to 1 gigabit per second on average. We could also here, for instance, I could also here present a comparison between these two, because it is always interesting to point out, okay, what are the pros and cons of each one of these technologies. For instance, regarding performance, both technologies do well for safety applications, and to some extent, they are both scalable. However, when we're talking about the wave standard, it is more geared towards vehicles, while 5G is geared towards any kind of network or even application. And here we can also point out that for 5G, we can have here some other technologies such as millimeter wave, in-band full duplex, MIMO, that will actually enable high transfer rates above 100 megabits per second, or even very low latencies between 1 to 5 milliseconds. On the other hand, we have here what? We have wave that almost there are no patents associated. We have also low latency, and as I've pointed out, it is actually an existing and a little bit more consolidated, given that it was has been having some developments over the years. And we can also here point out that it has actually been adopted or has been adopted by some governments for their vehicle networks. Regarding disadvantages, for instance, for 5G, we have here the deployment costs, because given that it's a new technology, there is always costs associated with its deployments, and also we have here a lot of patents. And for Wave, one of the disadvantages that we can point out is that given that it has been around for quite some time, we are getting a little bit skeptic if it will be the de facto standard adopted for this kind of networks. Connected vehicle networks can be broadly divided into these two types. That on the one side we have vehicle ad hoc networks, which have been around for at least 30 years, that comprise, for instance, a limited but important set of services between vehicles, such as message exchanging related to traffic situations, such as accident alerts, or even other cases involving cooperation between vehicles. Vehicle ad hoc networks actually comprise vehicle to vehicle and vehicle to infrastructure communications. On the other hand, we have the Internet of Vehicles that can be defined as a network of the future in which the integration between devices, vehicles, users will be actually unlimited and universal, overcoming the heterogeneity of system service applications and devices. It also brings the intelligence to the networks. What do I mean with that? The information will be distributed, shared, valued, and meaningful to both users and vehicular systems, authorities, and service providers. It is here important also to note out that in order for these kind of networks, in order for this kind of networks to be deployed on a real environment, the use of a trusted authority in order to register vehicles, infrastructures, and other elements, it's actually a must, because as I will also point out later on, security threats are actually a big concern when we are talking about networks themselves. This image here shows a vehicular ad hoc network architecture, where we can see here, for instance, a vehicle. We can see here a vehicle to infrastructure, okay, and that actually can provide internet connectivity. We have here a vehicle to vehicle, and we can have here also vehicle to roadside unit. What happens is that VANET, as I've mentioned on my previous slide, it's somehow a more simpler network, as it is not expected for this unlimited integration between thousands or even millions of devices, vehicles, among others. Here we have actually, when we are talking about the Internet of Vehicles, here I'm presenting actually two architectures that are somehow complementary in some sense. For instance, in A, this can be seen as a generic architecture, and it already integrates artificial intelligence. As we can see here, it already integrates artificial intelligence. Why? Because the use of artificial intelligence in IoV networks is one of those aspects besides the universal integrations that actually differentiates IoVs from panels. Another expected aspect of IoV is the integration with the cloud and its mechanisms to enable and facilitate certain computational paradigms, which we will actually discuss later on. At the top of this left-hand side architecture, there is the business layer, which actually means business value that will be built from applications. We have on the other side, on the right-hand side, we have another architecture that can be seen as a more detailed view of the architecture on the left-hand side. For instance, the perception layer can be split. The perception layer can be split into filtering and preprocessing plus data acquisition. And the representation is up to the application layer with the audio-visual user interface. Summarizing, it is here important to note out that IoV incorporates in their basic form new technological elements such as the cloud and artificial intelligence. And their use is actually expected and desired. When we are talking about challenges, I'm here basically, I'm here only these four, but the first three are expected of any network type involving many nodes with different computational capabilities and security mechanisms. For instance, heterogeneity is precisely the computational differences between cyber-physical elements connected to the network. Meanwhile, scalability is the ability to provide services even in the face of a very high number of nodes concurrently. Security can be seen as it's actually a very basic requirement for the smooth operation and orderly function of the network. And I will mention a little bit, I will talk a little bit later on about some security aspects of this kind of networks. The other important challenge is quality of service, because it is a complex, because we here, as we have mentioned, there is a lot of heterogeneity related not only to the nodes, but to the applications and protocols themselves. Each part will require, therefore, a given or a different set of quality of service requirements. Finally, we have also to mention here cooperation, which is about the willingness of every node in the network to share and process information so that a set of services are always available and reliable. Connected vehicle networks are still in the process of becoming popular. It is expected that there will be, of course, a lot of discussion about the advantages and disadvantages to the user in participating in this network, and whether it is there or he or they are actually willing to connect their vehicles to cooperate with each other. It is important here to keep in mind that it is yet uncommon, even with devices such as smartphones, for people to basically to be willing to share their devices' resources to the network with purposes not necessarily similar to their own. Here, when we are talking about computing paradigms, it is interesting to point out that the first two, cloud computing, fog or edge computing, or three, depending if you are considering the fog and edge separately, form the basis for future applications that will take full potential of the Internet of Vehicles. We can actually separate edge and fog computing for from a literature point of view, but they can also be considered actually the same thing. This decision of separating or not is rather methodological, has also it is also relative to the granularity of what we call the edge of the network, where vehicles and other devices are actually located. When we are talking about cloud computing, it is nowadays very well known. The cloud actually provides a pool of computing resources in a convenient, configurable, scalable, and on-demand manner, so that the maintenance and management effort is actually low to minimal. In its basic service provisioning models, the well-known platform as a service, infrastructure as a service, and software as a service are actually available. But of course, this is not only limited nowadays to these three provisioning models. We can have others such as function as a service. When we are talking about fog and edge computing, here it starts from a from the philosophy that data should be processed closer to where it's actually gathered. Besides not being necessary to send data to the cloud, it can be more secure at the edge of the network by considering how these fog or even edge ready devices are actually made. Applications that are actually needing low latencies or even real-time execution can be realized with fog and edge computing paradigms. Given these two or three base paradigms, the same can actually be applied to connected vehicle networks using vehicles as nodes, and whether computing entities in a cloud, these vehicles can be used as computing entities in a cloud cluster or edge or fog nodes, providing distributed networking, computing, and storage. To illustrate this, users can actually leave their cars in a mall or airport parking lot without paying, since their cars can offer computing power for services that those locations might actually be wanting to provide, and or even for other business purposes. These users can actually receive credit for letting their cars be used in these so-called cloud clusters. Whereas when we're talking about vehicular fog and edge computing, nodes can be used to build intelligence about the network itself and its users using machine learning in a distributed and regional manner. Information about the network and local traffic does not actually need to be computed on the cloud, as there is a long path to the cloud, putting, of course, unnecessary stress on the network. This image actually captures, the idea is to capture all this integration. We have, for instance, here On a far geographical location, we have the standard cloud. We have also here edge computing, in this case, mobile edge computing. We can have here a vehicular cloud on a parking lot. We can have here also a fog or edge computing, fog nodes. And here, for instance, someone may whether question if IOV, the Internet of Vehicles, would already mean these paradigms. And here the answer would be no. Why? Because IOV actually encompasses the interaction of vehicles with each other and with other devices that are not transportation infrastructure. IOV, nothing actually says about the organization of the network and the role of each entity in it. When we are defining a paradigm, we define a commitment of participation in the network for each node in it. A paradigm can be seen as an overlay network and further up the Internet of Vehicles, because it is a particular arrangement in which various services will occur. Here, we are basically comparing vehicular cloud computing and vehicular edge computing. And as we can see here, when we are talking about the geographical location, we see here that it is somehow remote for VCC, and for VEC, it is near the user. We have here, when we are talking about latency quality, we have here that it is low. In this case, that there is a high latency for VCC, and for VEC we have high latency quality, meaning that we have low latency. It is much closer to the user. When we are talking about communication, it is limited to the network infrastructure when we are using the cloud, and we have here high enough for real-time applications. When we are talking about computing power, we have here medium to high for VCC, and on the other side, we have high if achieved full expected integration. When we are talking about the cost, it's high for VCC and low because we are more granular and vehicle by vehicle built-in when we are talking about VEC. When we are talking about the dynamics, we have here that it is expected to be stationary for VCC, given that vehicles will be on a parking lot not moving, while for VEC it can be ephemeris, given that nodes can actually be moving at a very high speed. Of course, that we have here other also interesting parameters such as applications, advantages and disadvantages, where we can basically compare which ones can be more suitable for some given applications. When we are talking about limitations of these computing paradigms, it is here important to point out that this list here that I'm presenting is actually not exhaustive. For instance, when we're talking about high mobility and dynamic density, these ones are actually related to the fact that we are dealing with high-speed nodes, each with its own goal and time to stay in the network. In a matter of seconds, many nodes can split up, and the network that was once dense can actually now be very sparse. Services, applications, protocols have to be built with this dynamism in mind. Therefore, they must be resilient and timeless of protocols to keep up with the constant change in network topology, which is unstable by nature. In the case of vehicular cloud computing, it is actually more stability is expected. But when we are talking about VFC or VEC, it is actually the opposite. It is also foreseen, due to the Internet of Things paradigm, that there will be some integration, some aggregation with many devices, and zettabytes of data are expected actually to be exchanged. And for now, not even this new technology, the fifth generation technology, can cope with so much data, whether in vehicular cloud computing or vehicular fog computing. It is expected also that the maturation of those communication technologies that we have seen in the beginning, in this case, cellular, vehicle to everything, and wave technologies, would go hand in hand with the amount of data exchanged. But this is still not proven to be true at the present. Regarding the physical barriers in wireless environments, it is actually known that physical obstacles prevent nodes from connecting well. Buildings, unconnected cars, pedestrians, among others, are all physical obstacles that can actually and inevitably block electromagnetic waves at some degree. Therefore, points here 4 and 5 will go hand in hand in practice, and it is expected that this new technology, the 5G, will actually address some of these problems that have been pointed out in this slide. Now we are talking about security. Why? Because it is actually impractical to think of realizing any of these kind of networks without considering cybersecurity threats. And here I'm listing some examples that actually can affect these networks, such as malwares, onboard unit tampering, spamming and phishing, malicious node, denial of service or even distributed denial of service, masquerading, impersonation, cyber attacks, sniffing, eavesdroppings, and man-in-the-middle attack. Of course, that this list here is not exhaustive. If more information it's necessary, there is a recently published book that is called Intelligent Technologies for the Internet of Vehicles, that actually also contains more information about the use of artificial intelligence in the Internet of Vehicles, also addressing other security aspects in this kind of vehicles, in this kind of networks. Here, for instance, this image covers even more security problems than the ones I've mentioned on my previous slide. As can be seen here, for instance, for vehicular cloud computing security concerns, we have here trust, privacy, secure storage and computation, authentication and data integrity. We can have here, for instance, infrastructure security concerns, meaning secure storage, rogue nodes or rogue computation, tampering, hijacking. We can have here other, for instance, communication security concerns, such as jamming, signals, man in the middle, eavesdropping, denial of service, or even distributed denial of service, flooding, and spamming, and also for other elements of this environment. We still seek here to outline more specific security concerns given the characteristics of vehicular cloud and vehicular fog networks. For vehicular cloud computing, the biggest concern is isolation and virtualization. As is well known, in public clouds, several companies and users are sharing resources isolated from each other. A failure that affects isolation would mean compromising the data and other applications running on this vehicular cloud computing and putting and infrastructure, which would mean putting, possibly putting the vehicle owners at risk. For vehicle cloud computing, the most undesirable situation is any attack that denies the nature of this paradigm, such as specifically the decentralized and distributed operation of the node's computing resources. Communication disruption, whether by hijacking nodes, roadside units, or denying network access, is largely harmful to real-time applications. Regarding future directions, it is also important to point out that this list is not actually exhaustive. The technologies listed here make sense from a point of view of application development and the abstraction needed to provide flexibility in the network. Software-defined networks actually separate data and control planes of the network. These separations allows software-defined networks ready devices to work in multiple modes. This differs from having different devices for different functions, which is actually very costly and becomes unfeasible if in an ubiquitous networks with millions of devices, hundreds of protocols, thousands of types of data structures, or even communication standards. Specifically, if we are thinking of a vehicle as a node, their onboard units will need to be SDN ready to make it practical for them to participate in the network as a node that actually transmits data collaboratively. When we are talking about 6G, some early studies already point out how it might look like. Rates peaking up to terabits per second. Latencies will be less than 1 millisecond. The accuracy with which devices will be located can be little as 1 meter in open spaces and centimeters in closed Z spaces. Energy efficiency is also promised to be 100 times more than what we have available with 5G. Please have in mind that energy efficiency is a key in a ubiquitous connected environment where real-time and constantly sending data is present. Finally, we have here to consider serverless computing. Since it is a paradigm that allows applications to be programmed without a developer having immediate concern for the underlying infrastructure. Serverless computing is already made possible by the cloud. This paradigm is actually event-based. However, some current limitations need to be overcome, namely the fact that the cloud providers provide a limited set of events and functions. High abstraction and robust middleware can enable programmers worldwide to create intelligence and business values for networks such as VCC and VFC. Of course, nowadays, it is almost impossible not to talk about machine learning. Why? Because it has been proven to be fruitful in virtually every field. Concluding, some vehicular networks have been proposed in addition to applications. However, they are actually not that popularized. Connected vehicle network security is a complex and vital topic that the industry cannot put on the back burner, as is usually the case when deploying new technologies. Even if 5G and Wave are used concurrently, it is expected that the Internet of Vehicles will eventually be realized with the next cellular technologies, for instance, 5.5G or even 6G. And thank you for your time.
Okay, so thank you very much for your very interesting presentation and to bring this topic to our seminars. It is quite impressive, the work you have here, and it's quite promising. So now we will have a time for questions and discussion about the topic. I don't know if we already have some questions here from our participants. If you want to put a question, to ask a question, just raise your hand or write something in the chat. Just let us know that you are interested in ask a question, and we will be more than happy to listen your voice. Okay. Okay, we have a question here from Fabio. Fabio, you can ask.
Hello, I like your presentation a lot. I have a question about the remote countries like Australia, where you have big cities and then you have massive roads without connection. Is there some kind of handshake with satellite connection so the trucks can have this kind of networks in the city with other vehicles, and then when they go far away, they are still connected to the internet, sending and receiving data to the base?
When we're talking here about the Internet of Vehicles, when we're talking here specifically about infrastructure, we are considering more mobile networks itself. But this actually, it's not only limited to this kind of technologies, but the current developments are more focused to, the big issue here is that it is the data rate that we intend to offer for these kind of networks is considerably high. Maybe in the near future, it will be considered, for instance, having satellite connections, or maybe in the infrastructure, for instance, being it a roadside unit or other type of infrastructure that actually helps, provides internet connectivity to this kind of networks for this type to be having a satellite connection. But the vehicles themselves to the satellite, I can't foresee that happening in the near future, given the level, or at least the amount of data that we are expecting to circulate in this kind of networks.
The data will be more or less, when I have a lot of vehicles, they are exchanging data with themselves and with the network. If you have the vehicle on the outside road, the amount of data will be lower, right?
The goal is actually the opposite. It's not to limit the amount of data that is actually circulating on the network. We want for, because here, the goal is for the users to have a seamless experience. Doesn't matter if we are basically driving the car on the highway on the cities. That is actually the goal. That's why there is a lot of research and development for this to make this technology possible.
Okay, thank you.
Okay, good. So do we have more questions? Let me check here. Oh, Professor Camarinha.
Yes, thank you. So one question that your talk brought to me is, how do you see the interaction between these networks, then these vehicles, and the traffic regulatory authorities. For instance, the Portuguese traffic authority is making a large investment now with a new project to create more and more radars and other devices to manage the traffic and the accidents and so on. So how do you see the connection between the two flows of development?
The goal here, we are talking about vehicular, or at least one of the main applications, it's safety. When we are talking about safety, we need actually to consider not only the technology that is being added to the vehicles, but also, for instance, the intelligent transportation system. When we are talking about intelligent transportation system, we are talking about standardization bodies and all these regulatory bodies that actually will make use of this, of the amount of information that is actually being generated in these networks, so that we can improve, for instance, the traffic experience of the users. The other important point here that we need to consider is that, and given that that some of that actually happens nowadays, but this information is being collected using, it's not basically, that's not, the vehicles are not actually exchanging all this information and then sending that. You can have, for instance, the ITS itself collecting these informations using, for instance, cameras, checking the amount of vehicles that are circulating on the roads. But when we have these nodes, for instance, exchanging information and starting aggregating the amount of information, even on a remote site at a given moment, and sending this information to these regulatory bodies, it will help, for instance, reduce a lot of situations such as reducing pollution, for instance, finding new and better ways to improve the traffic in the cities.
Thank you.
Okay. Thank you for the question. So, do we have more questions from the audience? Don't be shy. Okay, I have here one question that Marco Becco sent. So, when do you foresee the deployment and implementation of these concepts in Portugal?
When we're saying about Portugal, I could, for instance, give one example. Actually, we have in Aveiro some that's like some sort of a smart city where it's actually some sort of a living lab, or where we have their 5G, we have their edge computing. They're also trying to build, for instance, these connected vehicle networks. This is actually already happening, but at a smaller scale. Okay. Of course, the goal, and it is also important here to point out that this is, for instance, the example of Portugal. Okay, many of these of similar projects are happening around the globe. If you go, for instance, for Singapore, there is also another consortium that is actually that built some sort of a test bed where many companies, automotive companies, are actually also interested in investing there. meaning that this is actually happening, and here in Portugal, in Aveiro. And I would, for instance, expect that from this experience of what is expecting in Aveiro, it will later on maybe in the short time be also, or at least start happening, or the deployment would of course start being made in other major cities. But of course we need first to create a very controlled environment and test if everything is working fine, and then to pass to big cities such as Lisbon or even Porto that are much complex to deploy and manage.
Okay, thank you. Thank you for your answer. So, questions from the audience. So based on your answer that you just did, I have a question. So since you are seeing Portugal or some cities in Portugal as living labs, you already have some lessons learned from that experience. Which are the main challenges to put this in place in Portugal, in the Portuguese case?
Actually, I'm aware of these deployments, but I'm not really I'm not really aware of what I'm not really aware of what is actually happening. I would have to. What actually happens is that even, for instance, this presentation, this research paper is a little bit futuristic in some sense, and there are a lot of aspects that still need a lot of deployment, a lot of development and research and development. I would say that maybe in the near future I would have more information, because for the time being I'm not. And the other thing that it's interesting to point out that is that anyone that is interested in doing research and development in this area can actually access this sort of living lab that is because it's being managed by Aveiro. Is it Aveiro municipality? Yes, it's being managed by them, and it's basically by sending an email. I myself will have to do the same in order also to because it would be interesting to start creating projects and having access to this equipment in order to materialize all these visions that I hear actually presented.
Okay, that's really nice. Okay, so we have a question from Sonia. So Sonia, go ahead.
Hello, and actually it's you talked about a lot of things, and one of the things that you mentioned, it was that one of your aims is interoperability in the network, and I want to know for recommendation for the other PhD student, is there any specific method that you recommend?
Sorry, I didn't got. One of the things that I mentioned was what?
One of the things that you are talking about that it helps. I want to know how it is helping for the interoperability.
But when you say interoperability of what? Of the network itself?
Yes, network.
But when you say interoperability between many devices,
no, specific in the vehicle, in the electrical vehicle. I want to know if did you think about this, because it is a new stuff that you have an idea about the.
Okay.
I want to know if.
When we are talking about electrical vehicles, actually, the technology that is being put into electrical vehicles, it's the most recent that there can be nowadays. And of course, I wouldn't actually just point or just refer to electrical vehicles. Maybe the most challenging there would be self-driving vehicles. Why self-driving vehicles? Because it is easy, for instance, even if it is a normal vehicle, we have there a human being that is actually controlling everything. Meaning that a human is basically by pressing a lot of buttons, looking around, he is always aware of what is happening. When we have an autonomous vehicle, then we have a huge challenge. Why? Because it's there where we actually need to apply most of these concepts. Communication among vehicles. A self-driving vehicle can have, of course, a lot of cameras, but then we need to have strong AI algorithms in order to recognize which objects are those, okay? And in real time, we need to make decisions if we continue or if we need to stop. There are, for instance, when you're talking about self-driving vehicles or autonomous vehicles, there are, of course, ranges, and we are actually a little bit nowadays. The most recent one, for instance, when you're talking about Tesla Autopilot, it is actually quite good. Why quite good? Because it actually drives itself around the city. Okay, it had just a little incident. Yes, I believe that it has a little incident. It crashed, but okay. If you are considering crashes, okay, there are a billion of crashes happening every day with while humans are on the wheel. But the systems that are necessary to enable autonomous vehicles are quite demanding. And for instance, technology advancements, when you're talking about machine learning, when you're talking about communication, we need to have, of course, a lot of, or even, for instance, the amount of cyber-physical elements, meaning sensors in a vehicle are increasing considerably. And even, for instance, code, lines of code. If we compare what we had before, like 10 years ago and now, there are like millions of lines of codes in just one vehicle. And when we have a lot of lines of codes, we have what? Bugs. Okay? There are a lot of challenges. We want, of course, to deploy, to propose new technologies, but on the other side, it is necessary also to correct a lot of bugs so that these new functionalities can actually be deployed correctly.
Thank you.
Okay, thank you for your question, Sonia. Now we have a question here from Sanaz about security. So, considering the complexity of this network and the different data formats that are going to be exchanged, could you please tell us what kind of framework you suggest to improve the trust and security within vehicles and infrastructure?
Okay, this is an interesting question. Actually, when we're talking about trust, trust is a very interesting aspect. Trust, for instance, trust and reputation. I actually have been doing some research related to reputation systems, and in order to improve trust, and where we can, for instance, consider what we call first-hand information. That is what the own node can actually acquire, and second-hand information, where is information that actually the other nodes are giving to me, so that I can actually be more aware of the environment. There is actually a lot of research that is still needed in order to improve trust among these among vehicles. Security. On the other hand, security. There are a lot of security mechanisms that have already been proposed. One of the challenges that I could consider there is that these so-called vehicles, or even nonetheless, for instance, if you consider new ones, given that most of these cryptographic protocols are computationally demanding, we need to propose more light approaches, so that even when we are using our cars, we can also use these same mechanisms. The challenge here that I would consider for the automotive industry would be to, for instance, to propose new and lighter approaches of such protocols, of such computing protocols, computing protocols, or some cryptographic mechanisms, in order to enable these devices to actually continue secure. Because nowadays we are now talking about quantum attacks. Given that we have quantum computers, now it's quantum attacks that will be zillions of years faster than the other attacks.
Thank you very much. I may suggest that the audience read some of the outcomes of the BECO project that is going on in Uninova. And I believe it can help to develop this trust, stability, and security between vehicles and vehicle infrastructure. Because this project, this Horizon project, is very interesting for this area. Thank you.
Thank you. Thank you for your questions, Sanas. So, do we have more questions here? No? Okay, I have here one question also from Marco. So, how would these technologies be able to cope with network saturation?
That's the same as saying bottlenecks in networks. Bottlenecks are a tough issue to address nowadays, because, for instance, when you're talking about 5G, okay, a lot has been promised. Some, of course, will actually be possible to implement. Okay, we have like from 100 megabits per second to 100 gigabits per second, and data rates, that's very good. But of course, when we are talking about Internet of Things, or even Internet of Everything, okay, and it's basically joining, or at least aggregating, all these subsets of Internet of Vehicles, Internet of Things, and things like that. And we start considering the amount of data, maybe we should process, or at least fuse information before we send. Why? Because that's like basically data processing or pre-processing that would basically enable to reduce the amount of data that actually we need to send. Because if every device starting sending raw data into the network, that will actually make things very, very difficult. It is a requirement it is actually a requirement to have some pre-processing prior to or after data acquisition and before we actually send the information.
Okay. Thank you. So, and based on this, what you just said, so this pre-processing, based on your experience, do you think that we should use the fog computing for this purpose, or we should push the designers and developers to try to do this even in the edge?
We can actually use, that's why we are here talking about computing paradigms, and the goal is for us to use them for something. And given that when we're talking about the vehicular edge or even fog computing, that they're actually much closer to where the data is collected, is gathered, then that would be a good point for pre-processing. Then we could, after pre-processing, we don't need to send all the data, we just need to send a subset of this input, a representative amount of this data to where it is actually needed. Yeah, we should for sure use them, because then we could send it, even after this pre-processing, we could send that to the cloud, okay? And even for further processing or even for storage.
Okay, thank you. So, more questions? So, so let's go. One more question. Okay, so I have one here. So, as you said, this is kind of a futuristic first approach, let's say. But of course, if you are pushing in this direction, you see a lot of services or possibilities that can be created on top of this, all these functionalities. Which services do you think will use this complex infrastructure in the first time? Because as soon as we have all this data available, a lot of services, I see that a lot of companies and a lot of institutions will try to make services on top of this. Which kind of services do you think will be the first to be developed?
Since we're talking about vehicular networks, for me, the priority would be to develop services that would enable to save human lives. Unfortunately, nonetheless, having a lot of, because nowadays cars, we have new cars with a lot of technology, for instance, collision avoidance and many of those other technologies, but there are a lot of accidents still happening. The goal for me here would be to use all this data to try to avoid it. For instance, we had that incident with one of the Portuguese minister car that was driving like at 200 kilometers per hour. Couldn't we avoid that? Maybe if somehow we knew that at a given location there were some maintenance operations over that location, the car itself would receive a signal stating that be alert because some operation is happening on that given road, and would first notify the driver, And if he actually does not take action, it would start automatically reducing the car speed in order to enable, because at a very high speed, doesn't matter if you are super fast. The car itself, we want the reaction time, it's very, very low. And maybe by reducing automatically the speed, it would have avoided or this and other type of accidents. Like what would be first the safety?
Okay, that's really interesting. That kind of approach. So, do we have more questions here on the audience? Let me check. Oh, we have a question from Professor Camarinha. So go ahead.
When you discussed the architecture that you were presenting, you mentioned that cloud is an essential part. In fact, more and more when we talk about everything interconnected, everything linked to internet and so on, we cannot avoid clouds. That's fine. The problem is that no matter how sophisticated are our networks and infrastructures, there will be always breakdowns. There will be always times that we don't have connection, that we don't have cloud, that we don't have internet. So how do you see the need to develop architectures and systems that can survive for a while without clouds, without internet?
The thing is that before the cloud, or prior, we did not have the cloud, and it was we were able to do a lot of things, okay, but actually the cloud helped it and is actually improving a lot of other things. I would say that in order, my suggestion there would be to do some other, to follow a different approach. Instead of removing the cloud, we would have redundancy or even fault tolerance. Why? Because we already know that systems, there are no perfect systems, okay? And even the cloud, even for instance, communications networks are not actually perfect, okay? But one of the biggest challenges of adding redundancy is costs, because in terms of infrastructure, we need to pay more in order to have this kind of redundancies. In the sense that there are trade-offs. We could say that there are here trade-offs. Because there are some applications that actually will only run in some sort of a cloud-based environment, because we don't always need to think of cloud as something that is very far away, okay? We could even think that, okay, the cloud can be not that far away, so that we can use, and even for instance, when you're here considering, for instance, VCC, that is a cloud, okay, that is not far away, can be, for instance, in Lisbon, when we're talking here about Humberto Delgado Airport, okay, it's not that far, depending on from where we are, it is much closer, and we can actually use it. And there are, if we're even considering, for instance, vehicular networks, they are like head-off networks, meaning that a path from what we can, instead of just using one path, we could, for instance, use a multi-path approach with one primary and a lot of backup paths in order to enable, for instance, communication to a given service. My goal here would be to look for more redundancy or even other alternatives in order to enable this service to continue, instead of just looking for other approaches, because the cloud is quite important nowadays.
Yeah, I agree that cloud is important, that we can benefit a lot from it. I also understand and agree that if we have a redundant infrastructure, that's better. But nevertheless, there are occasions that all the infrastructure is not available, even temporarily. All of us have experienced situations in which you go to some service or some office and they cannot provide you the service because at that moment the computer cannot connect to the network and so on. So we survive because we just have patience and so on. But in the case of vehicles, and especially autonomous vehicles, what happens if all of a sudden the infrastructure is down? So instead of investing more millions and more millions in redundancy, that takes time, perhaps you need also a different design approach in which you put more autonomy and more local intelligence in the vehicle itself so that it can survive for a while until it can again communicate, right?
That is true. Actually, that is true. Yes. What happens is that the vehicle itself, nonetheless, if we have the cloud, needs to be able to function. Okay, this is actually an essential part of this technology. But how? Because cloud can actually help us process some information, give us more information about A, B, or C. Okay, but given that the vehicle itself needs to be aware of what is happening, it needs to use a set of sensors in order to, for instance, to perceive the environment. Okay, this is actually important, and it's actually it's one of the main goals when we are talking about autonomous vehicles. Okay, and of course that this technology needs to be more sophisticated, because this is the goal itself of having an autonomous vehicles, apart from having extra services that can use this information to enhance the user experience or other additional services. I'm not sure if I was able to.
Yes, thank you.
Okay, thank you for the questions.
No,
So do we have?
Sorry.
Yes.
No, it's
So,
me. I am
Professor José.
coming late, very late, but it was something that I was really interested, by the way, Naercio, because this is something that we work in autonomous vehicles. There are some people here like Francisco that understand exactly the problem. The problem that Professor Camarinha raises is very important for us. Of course, we solve the problem because we really believe in local autonomies. So there are some things, and we see the need to deal with the internet or with the cloud from time to time. For instance, it's not that there are some parts that the vehicles can live without. There are other things here important, because if I was not here and I'm in doubt, the communication is between vehicle through the cloud, or they can communicate directly?
Actually, we have V2V, vehicle to vehicle, vehicle to infrastructure, and many other.
Okay. So this means that we can solve. You know, Camarinha, one thing that could be interesting, we exploit also, is that these swarms of vehicles, or some of them, we can also think this in terms of collaboration.
Yes.
See, because this is an important issue that is a very, I would say, dynamic, collaborative network in terms of, for instance, to solve certain problems. You see, I'm now thinking loud, but it's something that can be interesting. Another aspect that Sanaz mentioned, and the person that is with me in this project, that is Ricardo, is one fundamental aspect that, for instance, guys in the Fraunhofer are dealing with, suppose that we will have more and more the necessity to upload and dynamically change things in the mobile. For instance, one thing that we can imagine is I am in Almada, and anytime my car enters Almada, and this is not only for autonomous, can be also for my car. I say, my friends, no more accelerations here. So I change the program that controls the electronic ignition. But you see the problem of this. Safety, cybersecurity is crucial. Okay, and so this is why we were mentioning about this project here, because it's exactly how to control this in these directions. But there is a lot. This is a very interesting subject that you are bringing here, because there is a new way, and not only for the autonomous, even for our car, because then we can pass near the bridge and say, no, from crossing the bridge, my friend, you cannot go over 70, and then the system does not allow you. But
one approach, one of the things that some cars now have, they can actually read the speed signs on the roads. That would help.
Even my chariot can do this, so you see.
Yeah, what happens is that the vehicle now it's only suggesting, okay, that's like 70. It's up to you. You decide. Okay, I'm telling you that's 70, but you decide how you want to go. You would enforce that. Okay, that is 70. You can have like a tolerance like more 20. Above that.
That's it.
But this requires a lot of discussion, because it is somehow there are privacy issues. It is getting into other areas related in the society that should be like a debate, or should we actually change directly for safety reasons?
But
that's
anyway, it's still important, this communication, the work that you are doing. This is what I'm saying, and this is why I also brought the thing that even I can see the cars as a kind of for certain parts we can have a kind of column or a kind of interaction, a kind of collaboration between them that can be local, and then go and this. So this is something that we can talk about. So
okay,
yes, that's why I asked in the beginning that question about the interaction with the regulatory authorities, because what I notice is that, especially here in Portugal, our authority, national authority, at the moment they are investing a lot of money. They really put a lot of money in the infrastructure for speed control. Yeah. And okay, they claim that it is for safety reasons, not to collect fines from people, but they are creating a very large network with new technology on speed control and speed measurement. What appears to me is that this is one line of development in which the technology is going in fast, and there is a lot of money for this. The other line of development is the one that you presented, and I believe that the two should converge, should be together, not just separated lines of work.
Yeah, I agree with you, Kamaling. In fact, this is something, anyway, but this is the presentation of Naercio, so but there is a lot of things that this kind of presentation can trigger in terms of mobility, because this is connected immediately with the electrical mobility with the immediately, you see?
Yeah, that is true.
Okay, so we are reaching our time limit.
Exactly. I was thinking about the same. Okay, so I want to thank you all that asked questions and participate in this very good discussion. So now we have to close because it's 6:30, so it's time time to go. And one more time, thank you, Naercio, for your presentation and to answer all our questions.
Thank you for the opportunity. It was very interesting, this debate and even the presentation. Thank you.
Yes, thank you very much, Naercio,
you.
Andre. I just would like to remind you that our next seminar will not be on a Wednesday as usual, but it will be on Friday next week, on 19th of November. Yes, 19th of November. So we'll have Arnaldo Batista that will talk about signal processing in healthcare. So it's a different subject, but again, it's related to the general topics of cyber physical systems. So you are all welcome. So Friday, 19th of November. So good night.
Bye. Thank you. Good
Thank you.
night.
Thank you.
Bye.
Bye.